Hello, guys. How is everyone doing? Still holding up okay?
Hello.
Let's wait a minute longer. How's homework 2 going? Is it it's a little more challenging than homework 1, I would think, but hopefully you guys are doing okay on it. You can always ask the TAs for hints or use Piazza if you're stuck. Okay, I guess it's time to get started. So let's actually briefly review the last couple of lectures so we know where we're going. So what we did first when we talked about convergence of iterative algorithms for minimization or optimization more generally is that we first didn't really impose any conditions on the function, but then other than the fact that it's lower bounded and a minimum exists. And then we saw that we use a rule like Army-Host rule that actually decreases the function in every iteration. Then even if the iterates don't converge, every limit point of the iterates is a stationary point. So that's what we first showed. And then we imposed the condition of the Lipschitz gradient condition, right? And with the Lipschitz gradient condition, then we could be a little more relaxed about our step size choice. In fact, we can actually use a constant step size. And we showed in lecture 6 that even with a constant step size, as long as the step size is small enough as a function of the Lipschitz constant, so between 0 and 2 over L, where L is the Lipschitz constant, then you're still guaranteed that the iterates, every limit point of the iterate is a stationary point of the function. Okay, good. And then so last class we kept the Lipschitz condition, and then asked what happens if the function is convex, right? So the function is convex. We found that in that case, the iterates converge. Okay, so xk, basically all the limit points go to the same x star, and then the and the xk's go to that x star, which is a minimizer of the function, at rate 1 over k. Okay, so that was the idea. So when you impose convexity and the Lipschitz gradient condition, you get convergence. The x star may not be unique, again, but of course, all these x stars are going to be minima of there could be multiple minima for the convex function, right? If it's strictly convex, of course, it'll be unique. So then we went on to, again, the condition remains the same, that alpha has to be between 0 and 2 over L. So that's this condition that we had before. But the additional thing you get with convexity is that you get convergence, and you get a rate of convergence, 1 over L. Okay. And then we went on to see what happens when you impose something stronger on the function. So we said we make the function strongly convex, and that means that the Hessian is lower bounded by m times I, where m is some positive number. Okay, and under that condition, of course, strong convexity implies strict convexity, so the minimum is unique. But the other thing you get from strong convexity, which of course, yeah, and strong convexity we discussed was equivalent to the function being lower bounded by a quadratic like this. And under this strong convexity assumption, we concluded that the rate of convergence can improve dramatically. So it goes from inverse linear to an exponential decrease, right? So geometric decrease in that xn approaches x star geometrically as n goes to infinity. But in order to get that, you alpha being between 0 and 2 over m or 2 over l, or whatever you want to call it, is not enough. You need to make alpha a little bit smaller, okay? And then there's an optimal choice of alpha that gives you the best geometric rate of convergence, and that's given by this quantity, which is a function of the strong convexity parameter and the Lipschitz parameter. So, and actually it's this quantity here, m over 2m squared. And if you make this choice for your step size, alpha star, then you get this the best geometric, at least best upper bound on the rate of convergence of xn to x star. Okay. And then this ratio of capital M to M is called the condition number, and you want this thing to be close to 1 if you want a fast rate of convergence. If M is much bigger than 1, then in other words, the upper and lower bounds on the first order expansion, essentially Taylor expansion, the upper and lower bounds are vastly different from each other, then you get slow convergence. If they're close to each other, and they can actually be equal to 1, and the ratio can be equal to 1. So little m can be equal to capital M if the function is quadratic, for example. And in that case, you get the best convergence rate. Okay. So this kind of convergence, where in order to approximate the function to some level epsilon, you need an n that's of the order of log 1 over epsilon. Instead of it's 1 over epsilon, it's log 1 over epsilon. This is called linear convergence. Okay, right? But we can think of it as the fxn approaching f star exponentially fast in the number of iterates. And we saw an example of that. So in the case of this quadratic, little m is equal to capital M, and then you end up with the true rate of convergence actually is 0.5 to the power n, 0.25 to the power n. The upper bound actually gives you 0.75 to the power n. So it is actually it's not a tight upper bound. Okay, it's just an upper bound on the rate of convergence. And then we looked at a special case of a more general case of a quadratic. And then for that, in that case, of course, the Hessian is just this matrix Q, and so we know from the upper and lower bounds on this Z transpose QZ that that lambda min basically corresponds to the little m, the strong convexity parameter, and lambda max corresponds to the Lipschitz parameter for this case. And so the condition number is lambda max divided by lambda min. So for example, if Q was a multiple of the identity matrix, then lambda max will be equal to lambda min, in which case you get the best rate of convergence. Okay, and that's exactly what this example was. So any questions so far?
Excuse me, what we can have the rate of convergence is like 0.25.
Oh yeah, so this is on the square of this quantity, right? Xn minus x star squared is going as 0.25 to the power n. Is that what you're asking?
Yes.
Yeah, xn minus x star itself would just go as 0.5 to the power n, but the result was on xn minus x star squared, I believe. Yeah, this the upper bound was for the square. And I was just saying that basically the rate of convergence, the true rate of convergence of this example is actually less. I mean, the true difference is less than, and then what's predicted by the upper bound. So this was just to illustrate that the upper bound need not be tight. Okay. Any questions? Any other questions? All right. So let's start today's lecture. So in today's lecture, we're going to go even farther and get even better rate of convergence. Okay. And to do that, we'll introduce a method called Newton's method. And we kind of alluded to this maybe a few lectures ago. So what is Newton's method? It's also called Newton-Raphson's method. And you should have studied this in an undergraduate calculus course, right? So maybe 286 or some course, I don't know. Some of you are seniors, so you might be able to tell me if which course you might have seen a Newton-Raphson methods to solve finding a solution to a nonlinear equation. Anyone?
Robotics.
Robotics. Really, you studied in robotics, okay, but not in like 286 or something like that. No.
It's also taught in the numerical analysis course.
Oh, okay. All right, so let's actually briefly review that. So what's the idea behind Newton-Raphson's method? So you're trying to find a solution to a nonlinear equation gx equal to 0, okay? So the nonlinear equation could be something like, e to the x plus x squared plus 1 equal to 0, okay? So it's not, you can't solve for that thing in closed form. So you need a numerical method to solve it, okay? So what's a numerical method? How do you develop a numerical method to solve it? So the idea is as follows. You use the first order Taylor series expansion, essentially. So you can write gx plus 1. So it's an iterative procedure. So you write gx plus 1 as g of xk plus 1, sorry, is g of xk plus the gradient at xk times xk plus 1 minus xk. Okay? And what a goal is in Newton's method is that you want, at each stage of the iteration, you want to get close to, you want to make g at that iterate as close to 0 as possible, right? You want to get closer and closer to 0. So the thing is, so what you do is you say let's pretend like my iterate was chosen so that g of xk plus 1 is indeed equal to 0. Okay, and then what's the equation that you'll end up with for what xk plus 1 should be? So if you set this equal to 0, and this is, of course, this is an approximation. So what we're saying is that we're actually even thinking of this approximation as equal in trying to find an equation for xk plus 1 in terms of xk. Right, so assuming, so now here we have to assume that the derivative is not equal to 0. Okay, if the derivative is not equal to 0, then we can solve for this, set this equal to 0 and solve for xk plus 1 in terms of xk. So you get, this is xk plus, or sorry, minus, sorry, g of xk divided by g prime of xk. And that's exactly what Newton's method is. Okay, so very simple, straightforward. This is for functions that go from R to R, but this can be generalized to functions that go from Rn to R. And you can read the textbook for that if you're interested in seeing that generalization. It's basically the same idea. Okay. All right, so let's actually hear some plots from the book, some examples that are interesting to look at. So first, let's look at trying to solve for this function gx. You want to try to solve for this equal to 0, okay? That's the goal. So what does Newton's method do? let's so in this case, you start with x0. You have to start somewhere. You don't know that actually the solution to this problem, what the solution to this problem is, but in this case, you do know the solution to the problem, but that's in general you won't know. So the solution to this problem, of course, is that x. What should x be? X has to be 0, right? So let's see whether Newton's method will take us to x equal to 0 and how fast it gets there. So this is the solution that we're trying to get to, but we say we started at -1. Okay, so how should the next iterate be formed? Well, basically, if this is x0, then x1 is x0 minus g of xk, g of x0 divided by g prime of x0. So basically, you're looking at the slope, a line, okay, that has slope equal to the derivative at xk, and then you follow that line and see where it hits the x-axis, okay, and that'll be your x1. Okay, if this is not totally clear to you, just think about it this way. So if this equation implies that g of xk is g prime of xk times xk minus xk plus 1. So actually, you can think of it as going the other way around, that in order to get to g of x0, I can start at x1 here, and then make that the y-axis, y-coordinate equal to 0 at that point, and then follow the derivative and go down to this point here, okay, to get x0. So this relationship between x1 and x0 should hold. And then once you get to x1, again, you do the same thing. You take the value at x1 and then follow a line with slope equal to the derivative of g at x1 and see when it hits the origin. And that's your x2. Okay, so you're seeing that it's pretty quickly it's converging to the solution to this nonlinear equation. Okay, all right. In fact, if you can look at the iterates here. So in 5 iterations, you essentially get to 0 with the 6 decimal places accuracy, right? So very fast. So, but the problem is that Newton's method is not necessarily guaranteed to converge to the solution. So it can even diverge. Okay, it can go to something that is not the solution, but which of course you can verify in that case that it's not the solution. But it can also diverge. And here's an example of what happens when it diverges. And these are pictures from the textbook, so you can look it up in the textbook. So here's a case, and this is also a function actually that passes through the origin. So you would like your Newton method to actually end up here eventually, but you'll see here that I start with x0 here, and then from there I basically take the slope, go back down here to x1, hit the origin there, hit the x-axis there, go down there, and then go up, and x2 is now on the other side. So the magnitude of x2 is bigger than the magnitude of x1, which was bigger than the magnitude of x0. And we'll see that it keeps going up and diverging. Okay, so it's not, and this can happen if you especially if you start with an x0 that's far away from the solution, which you don't know, you may not know what the solution is beforehand, right? So if you start closer to the origin, then you have a better hope and you can probably try it out in this example. If you start closer to 0, then you will actually converge to 0. But if you start far away, you can diverge. Okay. So that's Newton's method. So how is Newton's method going to be useful to create a good optimization algorithm? That's what we're going to study today. So any questions? All right, so how do you generalize this notion to optimization? So in the optimization, the goal is to find an x such that the gradient of f of x is equal to 0. And now we're not operating in one dimension anymore. Okay, so x is n-dimensional. The gradient is also n-dimensional, right? But the same idea can be used. So here the goal in optimization is that you want to find an xk plus 1. You want the gradient to be 0 or close to 0. So you basically, given an xk, just like here, given an xk, you try to find an xk plus 1 such that the g of xk plus 1 is 0. The same thing you do here. You want to find an xk plus 1 such that f of xk plus 1 is 0 or close to 0, all right, to get a stationary point of the function. So again, use Taylor's approximation, just like we did in the Newton's method for solving gx equal to 0. And so Taylor's approximation in this case says that the gradient at xk plus 1 is the gradient xk plus the Hessian, now at xk, times xk plus 1 minus xk. Right? This is the first order Taylor approximation. Right? So this again gives us an equation for xk plus 1 in terms of xk. So what is that? Now now there's a matrix here that's multiplying. So we have to invert this matrix. So let's do that. So you get this is minus gradient, Hessian of f of xk inverse gradient. Of course, we have to assume that this is invertible, otherwise this doesn't make any sense. It's just the same as in the Newton method, we have to assume that the derivative is not equal to 0. If you hit a point that where the derivative is 0, in the Newton method, g prime is 0, then you will have to basically restart and go to another point. Okay, so that's so we're going to assume here, in order to invert this, that assume that this is invertible. Of course, we'll discuss a little bit later what happens when you apply Newton's method and you end up with a Hessian that is singular, right? It's not invertible. So we're going to assume that this is not singular for this iteration, right? So this is basically Newton's method for optimization. Okay. So is this like a gradient descent method? Kind of. So we can interpret it as a gradient method, generalized gradient descent method. We can think of for this as generalized gradient descent with alpha k equal to 1 and dk equal to this the whole thing basically. So you can think of it as alpha k dk as based with this matrix inverse gradient. Okay. Now, if it turns out that not only is the Hessian at xk non-singular, so it's invertible, but it's also positive definite. Okay, so if it's positive definite, then of course we can conclude that the gradient of f of xk times transpose dk is negative. Okay, which implies that it's a gradient method. Okay, so a generalized gradient descent method, right? So you can think of it that way, but although, I mean, there's no guarantee. So this is not like before when we used, say, a fixed matrix D to form a dk. So before we talk, in fact, that's something you're going to see in your homework as well. There in your homework, this thing there was a fixed matrix D, which was positive definite, right? You're choosing a positive definite matrix. for sure, or it could be dk, which is positive definite. Here, this matrix that you're multiplying, which is the Hessian, okay, is a function of xk, and it's a function of, I mean, your choice of f, and so it may or may not be positive definite. But if it is positive definite, then indeed this is like a step of a generalized gradient descent method. Okay. Any questions? So everyone understand what the procedure is? Okay. All right. Okay, so let's see why you might want to use this method. And it's likely used because of its convergence properties. Okay. But you have to be careful about using it. Okay, so we'll see why. So let's actually start to investigate the convergence of Newton's method. So let's say x star is the stationary point of f, right? So x star is such that the gradient of f is 0 x star. Okay. Then let's see what happens to the Newton iterate. Let's see how close it can get to x star relative to how at time k plus 1 relative to how close it was at time k. So we're going to again use, this is the same step we used last time when we looked at convergence for even actually we used it in the case of convex functions, strongly convex functions as well. So same thing, we expand xk plus 1 in terms of xk, right? So if we do that, I'll get the expression for xk plus 1 in terms of xk, which involves this. Okay. Now I'm going to write this in a slightly different form on purpose, and this kind of trick that we used even last class by exploiting the fact that the gradient of f is 0 at x star. So I can subtract out gradient of f at x star without changing anything. Okay, why do I do that? I do that because now I want to apply Taylor's theorem to this quantity. Again, it's just to make sure we understand what we're doing mostly. That's why I did it this way. So I'm going to apply Taylor's theorem to this quantity. Okay, and so the way I do that is I look at expanding gradient of f at xk in terms of gradient of f at x star. So if I do that, I get this expression here that this is the first order exact expansion for some beta between 0 and 1. Okay, so now let's plug that in, the Taylor expansion, to get an expression. So if we did that, we get that this is xk minus x star minus, I'm going to replace, so this I'm going to keep, of course. This is not what I can change with Taylor's expansion, but then what's inside there is going to be replaced by the Hessian. Times xk minus x star. Okay, and now I'm going to rewrite this because it's the norm of a difference. So I can take the difference in either direction. So I can write this as, anyway, I probably didn't need to write this step, but I'm going to write it anyway, just to be clear. And I get xk minus x star, and then minus xk minus x star. Okay. Right. So far, now all I've done is change the sign inside the norm, and that's not going to make a difference to the norm. And now what I'm going to do is try and absorb this term here. So I'm going to take this term kind of and absorb it into this. So the way I do that is by multiplying by the inverse of the inverse, which is the matrix itself. So I can write this whole thing as gradient, so Hessian of, not gradient, Hessian of f at xk inverse times Hessian at this spot minus the Hessian without the inverse times xk minus x star. Okay. So this is an n by n matrix. This is an n by n matrix. This is an n by 1 vector. So the whole thing is an n by 1 vector. I'm looking at this norm of this vector, but that vector is being formed by the product of two matrices and a vector. So I'm now going to recall what we talked about matrix norms. So if you look at a norm of a matrix, the norm of a matrix is defined this way. We saw this a few classes ago, right? Which can also be defined by taking the max for x not equal to 0, the ratio of these two. These are just vector norms, ax and x. So you're taking the ratio of those vector norms and maximizing for all x not equal to 0, and that's called the induced matrix norm. So whenever we talk about norm in this class, unless I say otherwise, it'll be the induced matrix norm that comes from the norm on the vector. Now, if A is a symmetric matrix, we saw in lecture 2, I think, or maybe lecture 3, I don't remember, that we know that we proved that the matrix norm is the maximum eigenvalue, which is also called the spectral norm of the matrix, right? Okay. Now, the fact that the matrix norm maximizes this quantity, right, means that if I look at this quantity for any x not equal to 0, that must be less than or equal to the matrix norm, because the matrix norm is the largest. Okay. And if I multiply x on both sides, then I conclude that this is true. And in fact, now I can actually include x equal to 0, because with x equal to 0, trivially, you have the left and right hand sides be equal to each other. So as long as I'm not dividing by 0, I don't have that issue of making x not equal to 0. So this is true for all x. Okay. So what this is saying is that if I look at the norm of A times a vector x, and A is a symmetric matrix, actually, this is true more generally, but we'll be using it for symmetric matrices anyway. It'll be less than or equal to the norm of the matrix A times the norm of x. Okay, so this is going to be crucial, because what I'm going to do is apply it to this product. Okay, so this is a matrix times a vector, and I want the norm of that. I want to upper bound that norm, and I'm going to upper bound that norm through a product of the norms of the matrices and the vector. And so this can be generalized. I can have a sequence of matrices, n by n matrices, that multiply x. Okay, and if I want to upper bound the norm of the product of the matrices times x, I can just take upper bounded by the product of the norms of the matrices times x. So we'll use it with just two matrices, because that's what we have here. We have some A and a B times x here. So let's say, what we're basically saying is that if I have A, B, X and take the norm, then I get the norm of A, norm of B times norm of X. Okay? Is that clear? All right. Okay, so how do we apply this? So basically, we're going to apply this to this product. So I have the norm of this guy, the norm of this guy, and the norm of this guy to upper bound this quantity. So that's all I've done here. I have xk plus 1 minus x star. Norm is less than or equal to the norm of the first matrix, which is the inverse of the Hessian. And then you have the difference between these two Hessians and the norm of xk minus x star. Okay, so I've now related xk minus 1 minus x star to xk minus x star, just like I did previously when we talked about strongly convex functions and convergence. Okay, so same step, but this looks a little more complicated. So what do we do now? So we want to now upper bound this quantity somehow. And so we're going to make an assumption. So we're going to assume that F is locally strongly convex near X star. Okay, it's just local. So around X star, if I look at the Hessian, then the Hessian is lower bounded by Mi with M bigger than 0. Okay, so this is like the strong convexity assumption we made last time. So last time we assumed that the function was strongly convex everywhere, but actually we didn't need to for the proof. All we needed was strong convexity around the X star that we were looking at. Okay, and in fact, even the Lipschitz condition can be restricted to be around X star if you wanted to. But anyway, so and the proof will go through. In fact, the book basically makes that clear right from the beginning in the proofs. Okay, so but to make the presentation a little easier in class, I just assumed that it was true for all X. Well, we can't make the assumption with the Newton method because basically, well, you could if you want to, but basically we're going to apply Newton's method in situations where we may not have that condition for all X. Okay, and so, but let's say if we have the strongly convex condition near X star, what happens to the convergence rate then? So that's what we're going to explore. So if I have this Hessian being lower bounded by M times I know that the minimum eigenvalue, right? And why am I looking at the minimum eigenvalue? The reason I'm looking at the minimum eigenvalue is because I want the norm of this matrix. The norm of this matrix, since it's a symmetric matrix, is actually equal to the maximum eigenvalue of this matrix. But the maximum eigenvalue of the inverse of a matrix can be related to the minimum eigenvalue of the matrix. Okay, so in this condition, actually, we'll focus on the minimum eigenvalue, and we know that the minimum eigenvalue of the Hessian under the strongly convex condition is going to be bigger than M, right, which is positive. Okay, so here we'll just give a result from linear algebra, which is very easy, and this is similar to other results that we. I think we did this for a square of a matrix, and we used it last time, and or 2 lectures ago. And so we'll now look at how the eigenvalues of positive definite symmetric matrix are related to the eigenvalues of the inverse of that matrix. So it turns out that if I have eigenvalues lambda 1 through lambda n for A, which are all going to be positive because it's positive definite, then A inverse will have eigenvalues 1 over lambda 1, 1 over lambda 2, and so on. And the proof is identical, really, in steps to the proof that we gave for the square of a matrix. And that is, you just use the fact that if lambda is an eigenvalue with eigenvector ui, then this condition holds ai ui equal lambda I ui, and just pre and post multiply this equation by A inverse. So this is A inverse A lambda I A inverse ui, and then basically this is equal to the identity matrix, and so you get lambda I inverse ui equals A inverse ui. And so you conclude now that lambda I inverse is an eigenvalue of A inverse with the same eigenvector ui. Okay. All right. So if you look at the matrix norm of A inverse, this is basically the largest eigenvalue of A inverse, which is going to be the inverse of the smallest eigenvalue of A by this result, right? So this result, the proof was just one line there. But this result implies that if I want to find the maximum eigenvalue of A inverse, I look at the smallest eigenvalue of A and take the inverse of that. Okay, all right, so far so good. Now, assuming that f is twice continuously differentiable, the Hessian is going to be continuous. If the Hessian is continuous, then if I'm close to x star, so xk minus x star is small, so in a ball around x star, say, then the minimum eigenvalue of, by continuity, the minimum eigenvalue of the Hessian at xk is close to the minimum eigenvalue of the Hessian at x star, which we know is bigger than m, which is positive. So basically, the minimum eigenvalue of the Hessian at xk we can assume is some gamma, which is positive. Let's say call it gamma tilde, say. So I want to use gamma for something else. Okay, then if we look at the spectral norm, the matrix norm, induced matrix norm for the inverse of the Hessian, which is what we want up there, we want to bound this guy. We want to bound this guy, so I want to find a bound for this guy. So that's the spectral norm of the inverse of the Hessian, and that inverse is related to the lambda min. So it's a lambda max of that quantity, which is the lambda min of the Hessian inverse, right? Oh, sorry, of the Hessian. So this is not lambda min of the Hessian at xk, and that is equal to, sorry, lambda min inverse, not lambda min. So that's equal to 1 over gamma tilde, which is, we'll just call that, define it to be some gamma, which is positive, right? Gamma tilde and gamma are both positive. We just use the fact that it's positive. That's all we need. Okay. Not equal to 0, basically. All right. Now we'll put another condition on the Hessian. Okay. And this is the kind of like a Lipschitz condition. It's a Lipschitz condition not on the gradient, but on the Hessian. But it can be defined very similarly as the Lipschitz condition on the gradient. So we'll call the Hessian L Lipschitz in some neighborhood of x star. So think of a small ball or some region around x star. And this is true. This is called Lipschitz. The Hessian's called Lipschitz. If I look at the Hessian at x and the Hessian at y and take the difference, that's less than or equal to L times the norm difference between x and y. Okay, same definition as that of the Lipschitz gradient. except we are applying it to the Hessian now for xy belonging to S. So what we basically assumed are two things in order to bound this. We assume that in the neighborhood of x star, the Hessian is L Lipschitz, and in the neighborhood of x star, F is strongly convex. So the Hessian is lower bounded by Mi. So if we do that, then we can upper bound this and this difference. Okay, and we're going to do that after the break. So let's take a short break, and then after the break, we'll see how we can use these conditions, the strong convexity and the Lipschitz condition around x star, to say something about to bound this quantity. Okay, so but any questions before we take a break? Again, this proof is a little bit hand wavy, and it's not completely rigorous in the way, because I'm kind of doing that on purpose, because again the convergence rate that you get for Newton, and that's observed in practice, this superb convergence rate, it really holds only when you're very close to the minimum. And the same thing happens as we saw in the example of applying Newton's method, to solve for gx equal to 0. And in the figures that we saw, that basically you have to be, if you're close to the origin, close to the solution, then it can be really fast. But if you're far away, things can be bad. So you really can only prove things about Newton's method under some assumptions like that, which is why it seems like it's a little bit hand wavy. But in practice, actually, this method can work superbly, and you can add some modifications to it, so to basically guarantee global convergence, not just local convergence. And we'll talk about that later. Okay, after the break. Okay, but think of this proof as more trying to explain what's observed in practice about Newton's method. All right. Okay, so let's take a short break, and we'll reconvene at 11:49. I guess 2 minutes from now. All right. Any questions so far? Okay. So now let's apply this guy, this Lipschitz condition, and this guy basically to get a bound on these quantities. Right. So basically, what we end up with is from the bound on the first guy is just gamma. Okay. That's for the bound on the inverse. Actually, it's not a bound; it's actually an equality. So this is just equal to gamma. So this is equal to gamma. And this quantity, I'm going to upper bound using L times the difference between these two arguments. So let's do that. L here times the difference between X star plus beta xk minus X star minus xk. Okay. And then the last term is just xk minus X star. Okay. Now, if you look at this difference between these two quantities, you'll see that there's a beta xk and minus xk, and then the beta x star and X star. So you put those together, you get gamma times L times beta minus 1 xk minus X star, and then the next k minus X star remains. Okay, but beta is between 0 and 1, right? There's some number between 0 and 1. Okay, and so this thing is so this is basically gamma times L. I can upper bound by gamma times L times xk minus X star squared. All right. Everyone happy with that? All right. So finally, we basically conclude that this is less than gamma times L times xk minus X star squared. Okay, so here's an interesting difference between what we saw last class and what we saw here, what we're seeing here. All right, so last class when we looked at this, let's look at the expression. So, yeah, so maybe let's focus on this. We have a relationship here that relates the square difference between xk plus 1 and X star. This was just the strong convexity result, not Newton's method. This is fixed step size, gradient descent. And we see that the square of the difference is related to the square of difference, upper bound of the square of difference at time k times this constant, right? And of course, if this thing has magnitude less than 1, you have geometric convergence. But what we have with Newton's method is even much better. And the reason it's much better is because now we're relating xk plus 1 minus X star to xk minus X star squared. And again, this is under the assumption that xk is already close to X star. Xk is close to X star. This thing is going to be really small and much less than 1, hopefully. And so in that case, I'm making xk plus 1 even closer at an even faster rate to X star. And we'll see why this is going to be faster than just geometric rate and just by expanding things out. So let's suppose x0 is close enough. I start, again, this is important. Newton's method, I have to start close to the solution. So if x0 is close enough to x star such that at x with x0 plugged in there, x0 minus x star times gamma times L is equal to, say, some delta which is strictly less than 1. Then what happens? Let's see what happens. So if I start close enough to x star so that this condition holds, then let's explore what happens at time 1. So at time 1, so I have x1 minus x star is less than delta, which is less than 1, times x0 minus x star. Correct? All right, good. So that doesn't seem very different from what I had for just within the result from last week for strong convexity. But that's what happens in the second stage. So x2 minus x star is going to be less than gamma L times x1 minus x star squared. But x1 minus x star squared is already less than delta times x0 minus x star squared. So this will be delta squared times x0 minus x star squared. Okay. Or maybe just to be less confusing, I'll write it in 2 steps. So that is x1 minus x star squared, and that's less than or equal to gamma times L times delta squared times x0 minus x star squared. Okay, but I take one of these x0 minus x star squared and multiply it by this gamma L, and I know that that's equal to delta. So this is equal to delta cubed times x0 minus x star. Aha. So how now I'm seeing now that in one step, going from x1 to x2, I've made my delta factor go from delta to delta cubed. Now, if I didn't have the squared relationship here, I would have just gone to delta squared in the second step. Let's see what happens in the third step. So x3 minus x star, it'll be gamma times L times x2 minus x star squared. But x2 minus x star can be upper bound by delta cubed with that. So now I get delta to the 6 times x0 minus x star squared, which is equal to delta to the 7 times x0 minus x star. Okay, so in 3 steps, my factor delta goes up to delta to the 7. And you can continue this or use mathematical induction and conclude that in n steps, what I'll get to is, anyone? How are 1, 3, and 7, if I want to complete that series, what's the next, what's the nth term? Yeah?
2n plus 1?
2 to the n minus 1, actually. 2 to the n minus 1.
Yes.
So 2 to the n minus 1 times x0 minus x star. So now you see that the n, the variable n, is sitting on top of 2 exponents there. It's a second exponent, basically. Right? So just delta to the n, I'm getting delta to something to the n. Right? So that's interesting. Okay, so now let's see what that means for the function approximation. So basically the idea here is that xn is going to, if I start close enough to x star, xn is going to get to x star super fast. Just in a few iterations, it'll be at the solution, essentially. Okay. And that's the same characteristic that we saw for Newton's method applied to the function gx equal to 0, right? Solving gx equal to 0. So, and if once you're close, you will get to the solution super fast in a few iterations, handful. Okay, and then let's see what happens to the function value itself. And this is what we did last time. We want to basically approximate the minimum value to some epsilon. So we need to look at f of xn minus f of x star. And again, we apply the strong convexity in the neighborhood of x star and expand out and basically use the upper bound that comes from strong convexity times xk minus x star plus m over 2 xn minus x star squared. Okay, and then this is equal to 0, and so this will be m over 2. Hold on 1 second. Sorry, not strong convexity. I have to use the Lipschitzness of the to use Lipschitzness of yeah, I'll have to use Lipschitzness here, but anyway, I need a constant here. So this constant, just like I did in yeah, so actually strong. Yeah, strong. No, it is strong convexity, right? Fx star. Yeah. So I'll need to use. That's right. Yeah. So it is strong convexity. It's going the other way around. So that's right. I'm doing xk in terms of x star. So that's strong convexity that I'm using. So f of yeah. So this yeah. Sorry, got a little confused there. So it is strong convexity. So this actually follows from strong convexity. So you get that this is less than m over 2 times xn minus x star squared. Okay, which is less than. Oh, actually, no. This term goes away. So sorry. Let me rewrite this. Okay, this is m over 2 times delta to the 2n 2 to the n minus 1 times x0 minus x star. Squared. Oh, okay, wait. I'm squaring things, so let me be a little more careful here. So first of all, let me just erase this, because that goes away. And then I'll have a little more room to write this down carefully. Okay, so what I have is delta. I need to square xn minus x star squared. So I need to take the square of this whole quantity on the right-hand side to get the upper bound. So that will give me 2. If I square this, then that will give me 2 to the n plus 1 minus 2. So okay, that's better. Times x0 minus x star squared. Okay, but anyway, the details don't matter so much as the fact that it's the value n on the right hand side is appearing 2 exponents up. Okay, which means that if I want to make this difference less than epsilon, then I need to choose n of the order of what? Is a log 1 over epsilon or what? Anyone? If I want to make this thing less than something times epsilon, what will I have to make n? What order should I choose n?
Is it log of log?
Log of log, very good. It's of the order of log of epsilon. Or log of 1 over epsilon. Actually, you can think of it as log of the log of the magnitude of log of epsilon, if you want, because epsilon is something small, smaller than 1. So log of 1 over epsilon will be some large. A log of epsilon will be some large negative number. Take the magnitude of that if you want. So it's basically of that order, right? And so you get a second order improvement over just using gradient descent with strong convexity. Okay, so you're getting order 2. This is called order 2 or super linear convergence, because log of 1 over epsilon is called linear convergence. This is called super linear convergence. Okay, and actually I can show you a plot from the book of where is it? Here. So this is actually a strongly convex function to start with, not just around x star. It's strongly convex everywhere basically, and you apply gradient descent to it. If you apply gradient descent to it, you go this way, and as you get closer to the minimum, basically it kind of slows down. So you're taking a lot of iterations. So this is still, much faster convergence than 1 over n. It's basically the geometric convergence, but it's still, compared to Newton does that in basically a handful of iterations. It gets to the origin. So it takes logarithmically fewer steps, okay, than just a regular gradient descent for this function. Okay. So again, if this was a local behavior, if this kind of strong convexity was a local behavior, then you might apply other methods that will get you close to the minimum. And once you're close to the minimum, you then apply just a few iterations of gradient of Newton, and you basically get the answer. Okay, so that's how you would exploit Newton's method. Okay, and in fact, that's what we're going to talk about next. Or actually, before we talk about that, we'll do a simple example. So, okay. So first of all, Newton's method, as I said, is super fast close to the local minimum if the function is strongly convex around that minimum. Okay. And actually, let's take the example of a function that is strongly convex, and a special case of that, a strongly convex function that's strongly convex everywhere, and that's a quadratic function with a q that's positive definite, right? So it turns out, let's see what happens if we apply this to this quadratic function, Newton's method. So in this case, we know that the gradient, we know this answer to this. In fact, you're going to actually do that in your first lab assignment as well as the same function that you have in your lab. And we know that this is Q. And the global minimum satisfies the gradient is equal to 0, which means that X star is Q inverse of B. Right? So we know all that. So what happens if we apply Newton's method? Let's start with any x0 belonging to Rn. x1 will be x0 minus the Hessian at x0 inverse the gradient of x0. So this is x0 minus the Hessian inverse, Q inverse, times the gradient, which is Qx plus B. So qx0 plus b. And now you'll see that the q inverse qx0 will cancel out with x0, and all you're left with is q inverse of b. So what's happened? I started with any x0, and what happened with x1 then? X1 became x star. So for this quadratic function, Newton's method converges in one iteration, one step. Okay, so that's basically the power of Newton's method. Of course, in order to apply Newton's method, you need the function. First of all, you need the function to be twice continuously differentiable, and you need to be able to compute that Hessian and the inverse of the Hessian. So in this special case, of course, this was all easy, but in general, okay, it may be difficult, computationally difficult. So that's why you may want to restrict your use of Newton's method, even if you can compute it. You restrict the use of Newton's method only when you're, close enough to the minimum. And how would you know that you're close to a minimum in practice? And in fact, you're going to have to do this when you program your optimization algorithm in lab 1. So somebody had an answer, yeah?
I don't know. It was just like before. Should it be x star equals to negative q inverse b?
Yeah, I believe so. Should be negative q inverse b here. Yeah. Sorry. Yeah. Good point. All right. So, yeah. So my question was, in fact, this should also be negative q inverse b. Okay. Sorry. So my question was, what was it? What did I ask? Now I've forgotten. Anyone remember what I asked? Then you can answer it. Okay. I guess it doesn't matter. Okay. So let's actually see what are some drawbacks of Newton's method and how you might fix it. So first of all, the inverse of the Hessian may fail to exist, right? So and that can happen if the Hessian is singular. And this can happen, for example, and that can happen other places too, but in the region of the function where f region of the domain, I guess, where f is linear, for example. If f is linear in some region, then of course the Hessian is going to be 0. So in that case, you're not going to have a non-singular Hessian. And it's not necessarily the gradient descent method. And that, as we see, I mean, even if the Hessian is invertible, the Hessian may not be positive definite. And so it may not even be a descent method. So f of xk plus 1 may be bigger than f of xk. Okay. And of course, just like any gradient descent type, any gradient-based methods, it may go to a local max. So all of these are not guaranteed to go to the local min, but although their descent algorithms, they will tend to be attracted by local min, and that was the capture theorem that I referred to from the book a few lectures ago. So it could go to a local max or a saddle point. Okay, so how do you try and address some of these concerns? So what you do is the following. You try Newton's method. If the Hessian is singular, or f of xk plus 1 is bigger than f of xk, so it's not a descent method, then use a different procedure, and that's what I'm going to describe now. And procedure B, okay, here you try to force the Hessian somehow to, or you modify the Hessian so that you force some kind of positive definiteness. So you add some delta k times I, identity matrix. So if you add a large identity matrix with a large enough coefficient, you should be able to make any matrix positive definite, right? So you can do that, right? So you choose a delta k such that delta ki plus the Hessian is positive definite. And in particular, you can make it not just positive definite, but you can also ensure that the minimum eigenvalue is bigger than some delta, which is positive. So then you can easily invert this matrix. Okay, so now you have this matrix that's invertible, okay, and use that matrix in a gradient descent step, a generalized gradient descent step. And that generalized gradient descent step, you will use that matrix, you'll use this matrix inverse times the gradient of xk. And since this is a positive definite matrix, it is a gradient method. So this dk transpose gradient is negative. So now we just use this dk essentially with a step size chosen using Armijo's rule. And Armijo's rule will guarantee that you decrease your value of, or don't increase your value of f as you go through the iterative. So you choose, and you can use other rules too that guarantee that, but let's say we choose Armijo's rule. Okay, now you keep doing that, but check. So check at the stage at any point if the Hessian were to actually become positive definite, then go back to Newton's method, because now you can invert the Hessian and you'll also get a descent thing because it's positive definite. So you go back to Newton's method and then just guarantee that, check to see if f of xk plus 1 is less than f of xk. So you're not applying Armijo's rule right now because in Newton's method, right? You're just making alpha k equal to 1. So you may not be guaranteed that f of xk is less than f of xk plus 1 is less than f of xk. So you go back and check, okay? And then you continue Newton's method as long as these conditions hold, as long as okay, and as soon as one of these conditions stops holding, you go back and go back to B and modify your Hessian to make it invertible, and then apply Armijo's rule. So clear? So this way, what happens is that you're getting the power of Newton's method, but you're not diverging from the minimum. Okay, you're still trying to get towards the minimum. Okay, but you're going to get to it much faster than if you just applied regular gradient to start with without any Newton steps. Okay. Again, all of this, I mean, this whole lecture was a little less rigorous in a way. It's more of an engineering. It's more engineering methods rather than. Don't think of this as a rigorously mathematical approach. This is basically a lot of tweaking that's done and it's done primarily to make convergence faster. So for computational reasons, really. Okay. All right. So any questions? Almost out of time.
So is Newton's method the best approach for optimization as long as the condition holds, or is there even better one?
Oh yeah, we'll study more approaches.
Okay.
Okay. That yeah. So there are momentum techniques and so on. So maybe we'll get a chance towards the end of the course to talk about other methods too. But Newton's method is very powerful. Okay.
Thank you.
So but as long as you can, first as long as the function is twice continuously differentiable and that the dimension is small enough that the inversion is not that hard. Now there are modified Newton's methods, quasi-Newton's methods that allow you to improve the computational complexity of the Newton step. So there's a whole discussion about that in your textbook. Okay. All right. So if there are no other questions, any other questions? Anything about the homework? Okay. All right. So let's stop, and I'll see you guys next week.